Okay, so let's look at tutorial sheet 2. And the first question in section A is saying a temperature sensor measured at 7.5 degrees Celsius inside the body. A pressure transducer measures a blood flow force of 4.2 newtons directed 60 degrees to the vessel wall. A, which of these is a vector and why? Which of these is a vector and why? After part B is saying represent the force vector using components along the horizontal and vertical. Represent the force vector using the components along the horizontal and the vertical. So to answer part A simply, we're just going to say the vector in this case is the blood flow force. Because if you look at the blood flow force, we define a vector as a quantity that has both magnitude and direction. And if we look at how they've given us the blood flow force, they've said the blood flow force has a magnitude of 4.2 newtons directed at 60 degrees to the vessel. So it is having both magnitude and the direction. Whilst if you look at the temperature, it has only been given as 7.5 degrees Celsius, of which it's well known that temperature is a scalar quantity by now. So to simplify the question, but A, the vector here is the blood flow force. But B is saying represent the force vector using components along the horizontal and the vertical. So since we've identified our force now, what are we going to do? Let's represent it using its components in the vertical and the horizontal axis. So how do we do that? We learned how to convert a vector into its components, or how to resolve a vector into its respective components. If you didn't, or if you haven't watched that video yet, you still have a chance. You go and watch it on my YouTube. So part A, this was question 1. Part A, we said the blood flow force is the vector. Blood flow force, and blood flow force has been given to be a force of magnitude 2.5 newtons directed at 60 degrees to the blood vessel. So what are we going to do? Let's resolve this this vector into its respective components. So to resolve it into the x, we know to say we're going to say it's this same force cos its direction from the positive x-axis, which is theta. Of which, for us to resolve it into its y component, we're going to say the magnitude of the force sine the direction of the vector or the force from the positive x-axis, or with respect to the positive x-axis. So I'm going to say this will be equal to 4.2 cos 60. Cos this one is 4.2 sine 60 degrees. And the final answer for the x component of this blood flow force is 2.1 newtons. 2.1 newtons, whilst in the y component, I have 3.637 newtons. So these are the respective components of our vector in the x and the y component, of which if you wanted to write them as a unit vector, you're going to say the force or the vector is going to be equal to 2.1 newtons. I, this is in the x-axis, plus 3.64. Let me just say 64 newtons. J, like this, in the y-axis. So these are the components. We've written our blood flow force as a component. Okay, let's go to question 2. Question 2 is saying, during muscle contraction, the biceps apply a force of 120 newtons at an angle of 40 degrees above the horizontal. Resolve this force into vertical and horizontal components. That's question for part A. Part B is saying which component contributes more to joint lifting. So this one, part B, is we have to understand the question in order for us to answer this one, because they're saying during muscle contraction, the biceps apply a force of 120 newtons at an angle of 40 degrees above the horizontal. Resolve this force into vertical and horizontal components. Which component contributes more to the joint lifting? So you are lifting the joint. lifting the joint up. So which force is contributing more to joint lifting? Okay, so that's question B. First things first, let's answer question A, or part A of the question. Part A of the question is saying we have been given 120 newtons of a force. And this force is directed at 40 degrees above the horizontal. So this is 40 degrees above the horizontal, which means this 40 degrees that we've been given has been provided with respect to the positive x-axis. Which means from the positive x-axis, from 0 to where this force is being applied, we have a direction or an angle of 40 degrees. So let's resolve this guy into its respective components. That's the x and the y component. So for the fx, we're going to say this is going to be equal to 120 cos 40 degrees. Whilst for the y, we're going to say this is going to be equal to 120 sine 40 degrees. Okay, so I'll punch this into my calculator. I'm getting the x component as 91.92 newtons, whilst the y component is 77.160 newtons. Okay, so that is the x and the y components respectively of the force that is lifting the biceps. So they're asking another question, which is question B, to say which component contributes more to joint lifting. So joint lifting, I said this question expected us to understand the question. Joint lifting is primarily going to involve upward motion against gravity. That's why you're lifting that joint. And we have these two forces. There is one force which is acting in the horizontal axis, and there's one force which is acting in the vertical axis. So since joint lifting is going to primarily involve the upward movement of your joint against the force of gravity, what are you going to conclude? We're going to conclude that the vertical component is the one which is doing more job in lifting the joint that we have. So in short, let me just write it here to say the one that is responsible for lifting this joint here will be the vertical component. The vertical component, and why is that? Is because joint lifting involves upward movement. Upward movement against gravity. So that's the answer to question B. And if we answer that part, that means we are done with question 2. We can move on to the next question, which is now question 3. So question 3 is telling us to say two physiological vectors representing nerve impulses in two different neurons are A, 3I plus 4J millivolts, B, saying negative 2I plus 5J millivolts. Question A, determine the resultant vector R of vector A plus vector B. B, find the magnitude and direction of R. So this question is also very, very, very simple. What are we going to do? We're going to go to our board here and say question 3. Okay, question 3, we have two vectors. So we have vector A, which is 3I. So this is vector A, 3I plus 4J. This is in millivolts, which is the unit of measurement for measuring electric impulses. Then we have vector B, which is negative 2I plus 5J. This is also in millivolts. So question A is saying we should find the resultant R of vector A plus vector B. So what are we going to do? We're going to add these theoretical, the analytical addition of vectors. Of which by this, what do I mean? We are having two components on each of the two vectors. So that means my R is going to be equal to what? My R is going to be equal to or is going to be divided into two also. I'm going to have Rx and the Ry. This is how I'm going to find the resultant of these guys. And Rx, this one is going to be equal to Ax plus bx, whilst my ROI is going to be equal to AY plus B y like this. So this is what is going to give me the addition of this. All this by the x components are represented by the i's here, whilst the y components are represented by the j. So let's add these guys. So I'm going to say my r is going to be equal to I have ax plus bx, this plus ay plus b y like this. Remember, these are vectors, so we have to show them with arrows on top. Okay, so this is going to be equal to ax is 3i, 3i plus negative 2i plus ay is 4j plus 5j. What am I going to have? Let me just rub this. Let me create some space there. Okay, so we have 3 plus negative 2. That's going to give us positive 1. So our r is going to be equal to 1i. I struggle to write a straight small letter I. Okay, so 1i like that, plus 4 plus 5j, this is 9j. So that means the components of our resultant vector r are going to be equal to what? To be equal to 1i plus 9j. And question B is asking us to find the direction and magnitude of this vector. So in order for us to find the direction of this vector, are going to involve the Pythagoras theorem. I'm going to say the resultant r is going to be equal to x squared plus y squared. So this is the same as having 1 squared plus 9 squared. This is going to be equal to 1 plus 81, like this. And I'm having 82. That means my magnitude of r is equal to 9.06 millivolts, like this. So that is the magnitude of our r. And they've asked us to say we should find also the direction of this vector. So how are we going to find the direction? I'm going to use the arctan to say theta is equal to the tan inverse of the y component over the x component. This is going to be equal to what? It's going to be equal to the tan inverse over ROI over RX, of which ROI is 9 over 1, like this. So the tan inverse of 9 is going to give us theta, which is equal to 83.66 degrees. So our direction of this vector is 86.66 degrees. Hence, we've answered the whole lot of question 3. We can now move on to the next one, which is question 4. So question 4 is saying a vector field inside a brain region is given by vector E being equal to 4i plus 3j in millivolts per millimeter. Calculate the magnitude of E. Determine the angle the vector makes with the x-axis. Explain the clinical significance of directionality in EEG vector signals. Okay, so but C is theory. You just have to read the theory, understand, and give your answer. There's not much of physics in there. So let's solve the first two parts first. That's question 4. Question 4, we've been given vector E. Vector E is equal to 4i plus 3j. Okay, and this one has been given in millivolts per millimeter. So they're asking us to say we should calculate the magnitude of E, of which the magnitude of E with modulus or absolute value there are going to be equal to what? Equal to Pythagoras theorem of EX squared plus EY squared. This is going to give us the following. We have the x component as 4, so 4 squared plus 3 squared. This is going to give us 16 plus 9. 16 plus 9 is equal to 25. So the magnitude of E is actually equal to 25 millivolts per millimeter. That is the final answer for the magnitude of E. Now they are asking us to say we should determine the direction, the angle that the vector is going to make with the positive x-axis. So how are we going to do that? We're going to do or to apply a similar method. Say theta is equal to the tan inverse of EY over EX. Okay, so there's one thing that we're supposed to take note of when we're dealing with vector addition or when we're having two components of a vector. The direction of the components actually gives us a clue of which quadrant your vector is lying in. So it depends if the x component is negative or positive, or if the y component is negative or positive, it is going to give you a clue. It is going to show you the direction in which that particular resultant is actually going to lie in. So if both of the components are positive, like what we have here, that means they are both lying in the first quadrant. And we know to say in the first quadrant, theta is calculated directly. It was going to be different if we had a negative x, because if x is negative and y is positive, that means we are dealing with the second quadrant. And theta in the second quadrant is equal to 180 minus alpha. So we have to apply those rules even when we're dealing with vector addition. Check the sign of each of the components that you're having in both the x and the y components, as it is going to give you the actual clue of where your vector is lying or in which quadrant your vector is actually lying in. So let's say this is going to give us, since both are positive, that means we can calculate theta directly here. It's the same thing I did on question 3. So theta is going to be equal to the tan inverse of 3, which is in the y-axis, divided by 4 like this. So sorry, this is the tan inverse like that, of which the tan inverse or the arctan of 3 over 4 will be equal to 36.87 degrees. 36.87 degrees. So which means the angle which this vector E is making with the positive x-axis is just actually 36.87 degrees. So they're asking now, question C is asking to say, what is the clinical significance of the directionality in EEG vector analysis? So the directionality now of these EEG vector signals is very clinically significant. In which way? First, what do we mean when we say EEG? It's also known as electroencephalogram. Yes, electroencephalogram. It's a very important machine which measures the electrical activities of the brain. If you've checked those people who are admitted in hospital, they will put something in your head which is having, I don't know how to describe it unless I had a picture. I don't know how to actually describe that thing. And it is responsible for picking the electrical activities that are in the brain. So what is the importance now of the directionality of the EEG vectors in the brain, or the clinical significance of those EEG vector signals? One of them we can mention is to localize the brain activity. So I can say localization. Brain activity. Localization of brain activities, of which by localization of brain activities, I mean it mostly helps to identify the origin. It helps you to identify where those electric signals are going to originate from, and also how they are going to propagate against the different regions of the brain. And for using this, you can actually be able to understand or be able to determine or to figure out where there is abnormal activity in the brain, or if there is a fault in the electrical activity of the brain using the directionality of the EEG vectors. That's one of the very important points. Sometimes you can also help us to to monitor neurological disorders. We just say monitor neurological disorder. Monitor neurological disorders. So how does it monitor neurological disorders? Because mostly it keeps on monitoring the activities of the brain. So, or the electrical activities of the brain to be specific. So whenever whenever there's a sudden unexpected change in the direction or strength of the vectors themselves, the EEG vectors, it is able to indicate to you, the health personnel, to say there's progression or improvement in some conditions, some mental conditions, some neurological conditions, such as we can talk about epilepsy sometimes, brain tumors, or TBI, the traumatic brain injury, or even stroke itself. So that's also one important. I can mention a lot of them, even surgical planning, but for now we can just mention this, and we can say we are good to go. When you can write them, just look them up and write a lot if you'd love to, but let's not waste on time on that theoretic question. Just look it up so that you are able to answer such questions when they come in your exam. Let's look at the fifth question, which is question number 5. Question number 5 is saying an ultrasound sends a wave at 30 degrees to the vertical. The wave travels with a speed of 1,500 meters per second. Question A, resolve the wave's direction into horizontal and vertical component. Question B, explain how this helps in forming a 2D ultrasound image. Resolve the wave's direction into horizontal and vertical component. B, explain how this helps in forming a two-dimensional ultrasound image. Okay, so this is question 5. Question 5, they've given us a wave with a speed of, so I'll put speed here, 1500 meters per second. Then they've given us to say it has an angle of 30 degrees with the vertical. So what does that mean? That means I have my vertical axis here, and there's this theta, which is here, which is 30 degrees like this. And that is the direction of our ultrasound, our ultrasound wave. So it is making this angle with the vertical and not the horizontal. So that's one thing we're supposed to take note of. And they've told us to say we should do what? We should resolve the wave's direction into its horizontal and vertical components. So what are we going to do? We're going to say there's Vy and Vx, and Vx is in this axis, whilst Vy is in this axis. So what do we do when we've been given the theta not relative to the positive x-axis? We're going to calculate the direction of this vector, or we're going to resolve to the components using this same theta that we've been given, which is 30. But there are two ways in which we can do that. It's either we can use this 30 to find the direction of this vector from the positive x-axis, which is this guy that is here. We can find this angle, I'll call it alpha, or we can still use this 30 that is here. So how are we going to use this 30? Well, we mentioned to say when resolving a vector into its components, you are going to apply a cos to the component which is adjacent to the theta. Very important. You have to understand that statement, and you will never go wrong with it, and you will never have trouble resolving vectors. If we have been given theta here at this point, that means, we should only know that the component which is going to carry a cosine will be the one which is adjacent to the theta. And in this case, the one which is adjacent to the theta is not the x-axis, no. It is the y-axis, because the 30 is adjacent to the y. So that means the y component is going to have what? It's going to have your vector cos theta, of which this theta is the angle that is given adjacent to the x component there. Then the one which is away from the theta is going to carry a sine. Or if not, you're going to find this angle alpha that I've given you here. Then you're going to use this alpha to find to resolve this vector into its components. But when you find this one, you're going to remember that even this alpha that is here is adjacent to the x component, so which means the cosine is going to go back to the x component. As simple as that. That means you've cracked the secret of resolving vectors into their respective components. So I don't know which one is which, because this one is 90, so this is 60 degrees here. So we can use either of these and it is going to give you the same answer. But this one is very interesting. I wanted you to understand this one, to say the one which is adjacent to the theta is the one which is going to carry cosine. Hence, you should always apply that knowledge wherever you go. So I'm going to say my v cos theta, which is my v cos 30 actually. Let me even rub this diagram. Is going to be equal to 1500 cos 30 degrees. And this is going to give me how much? This is going to give me 1299. 1299 meters per second. Whilst this other one is going to have 1500 sine 30. This is the x component, 1500 sine 30. And this is going to give me 750 meters per second. So you should try this at your own free time. Find the difference between 90 and 30. You find 60 as the alpha that I earlier drew. Then use that alpha to find the directions. Apply the cosine on the x component. That means you have 1500 cos 60 on the x component. Then you have 1500 sine 60 on the y component. It is going to give you these exact same answers in both the x and the y components respectively. So that was question A of, or that was part A of question 5. And question B, he was telling us to explain how this is going to help in the formation of a 2D ultrasound image. So how is this going to help us in the formation of a 2D ultrasound image? So one thing you're going to notice is that it is going to help in image reconstruction, where the principle at which ultrasound machines work, they usually map signals based on the direction of the wave. They'll be marking their signals based on the direction in which the wave is traveling. So by resolving the wave components, the machine is going to be able to determine where the echoes are actually coming from in two-directional space, hence giving us the depth and the lateral position of your ultrasound. Very important, this thing. Then they can also help us in reduction of artifacts. Very important in that one. Sometimes we can also talk about the beam steering and focusing. Spatial mapping, I've already talked about that one. Also improved reconstruct or resolution. They improved the resolution of your two-dimensional image, because the wave's directionality is going to the wave's directionality is actually going to ensure accurate interpretation of the reflected signals, and by that it will to reduce the artifacts that I've already talked about and improve the resolution of the image, which is very important actually for you to be able to visualize the anatomical details. So mostly ultrasound images are used in fetal structures and also observing movements in the chest, cardiac motion. So using this principle and some of the points that I've talked about, you can improve the formation, or it's going to help in the formation of two-dimensional ultrasound images. And yes, that's it on question 5.